So I was studying this matrix determinant stuff, the Gauss elimination. I think I understand a little bit more now, but I couldn't. I copied some code and tried a bunch of different ones, but I don't understand fully 100% what's going on. And I think I'm gonna study more about this in the next coming days. I found this playlist here from this guy. I think I'm gonna watch this playlist. And it's gonna be good because a lot of data cleaning and data analysis and machine learning has to do with matrix multiplications. So it's gonna be good to review this stuff that I forgot a bunch. And yeah. So this was what I was doing right now, and I think now I'm gonna study. I won't be here for long, I think, but I'm gonna study these topics here that I have from the data engineering tests that I did on Turing, and I took the notes down. And I'm also going to choose a Kaggle competition, I think, for the next time I stream. I'm gonna divide on 1 hour, 1 hour and a half for trying to solve katas, and then the rest of the time I'm gonna try to do these competitions here to practice data cleaning and data analyzing data. Should do the Turing complete tests.
Hello guys and welcome to Python programming tutorials by Amul's Academy. Determinant matrix. Need to mention a 2D array. I need to take the square matrix. If you take matrix which are not square, right? This is the B. If I do that, it is determinant of matrix manually. So B into I, 5 into 9, to 7. 36, 6, we'll get minus 6 into minus 2, that is plus 12. So here 12 minus 9 is nothing but 3. If you are using the determinant function, then it is simple. We need to take the matrix first, then we need to use the determinant function, right? Okay, so this is about the determinant function in linear algebra.
I think I will study the playlist. I'll watch the playlist and then I'll think about the problem again. Next time I do the Kaggle, I devote some time again to trying to solve the challenge. And then if I can't do it after that, I think I'm just gonna see the solutions from other people and move on because I don't have a lot of time to solve it or to study this. Even though, yeah, maybe I should take more time on this one because matrix is really important. Yeah, so I probably should try to solve this one specifically.
Having learned
and then the other ones I take last time.
the direct method for solving simultaneous linear equations, you will notice that the order in which the equations are presented to the solution algorithm has a profound effect on the results. This ordering is what we call pivoting. Okay, so we're going to discuss pivoting. Very simple, we just simply use swap modules. So you have this function here, swap rows, swap columns, and what it does is to swap two columns. In this case, two rows. So if you have the first and second, you want to swap, okay, you can swap it. Then you will know that some problems or given you have the old that still the same, identical. Okay, so these two, the elimination, which is quite much time we get the okay, and here.
So I think I'm gonna study these topics here and I'll watch the playlist off stream. I probably won't be streaming in the next few days, so I'll have time to study this stuff. Okay, so I think I wrote this down just because I didn't know what it was, but now I know. I think NoSQL bases are database formats that are similar to JSON formats where you have key value pairs. And they're, I think they scale well horizontally, no, vertically. And databases like SQL scale well horizontally. But I'm not sure. Maybe I should search this again. Maybe it's the other way around. So SQL is structured query language. I hate this stuff when they put this cookie stuff. Okay, so SQL is vertically, probably. NoSQL, NoSQL, SQL, horizontally. So SQL is vertically. I should probably write this down here. Spark, if I'm not mistaken, is for large databases, but I don't remember really well. I've seen many articles in many different websites that repeat that the fact that SQL databases are scaled vertically by adding CPU memory, whereas NoSQL databases are scaled horizontally by adding more machines that can perform distributed calculations. For example, in this article, the thing is that I can't understand why. The major difference between SQL and NoSQL, beside the scalability issue, is that SQL is stored in tables, where NoSQL is stored in different ways: key value, graph, XML. You can't seem to understand the connection between these two facts, scalability and storage strategy. These seem like unrelated things to me, probably due to lack of understanding. Both NoSQL technologies and SQL technologies, for lack of a better term, have important roles to play nowadays. As both articles point out, the discussion is somewhat reminiscent of hierarchical databases versus relational databases. Once upon a time. I disagree with the scalability differences. The discussions leave out technologies such as Hive, Bristol, DB, and BigQuery, which are based on highly scalable technologies in the spirit of traditional RDBMs. Major differences are acid compliance and data structure. The first is a burden that relational databases carry for both better and worse. Definitely handy for financial transactions, but at the cost of overhead for other purposes. The second is an area where traditional databases are moving towards better handling of unstructured data, with direct support for nested tables, JSON and XML formats. However, structure is important, as legions of data scientists probably learn the hard way as they interact with data. Another thing that I think I'm gonna do as well is finish the boot space project, because I managed to install the VM and all this stuff on the VM. So I think I'm gonna clone the repo from the VM with the project from build space and finish that project for the rest part and try to deploy on the testnet. I think that's gonna be good. I'm still not sure if I'm gonna do this on stream or off stream though, because I have to do this data. Maybe after I finish studying or doing a few competitions on Kaggle and passing the tests, hopefully passing the tests on Turing, then I can focus on finishing the project on Web3. Large scalable key value databases have been designed with horizontal scalability in mind. That combined with the lack of pure asset properties facilitates rebalancing the data for new hardware, assuming you designed the database correctly, and that can be a large assumption. Databases such as Oracle, DB2, and Teradata have supported parallel processing literally for decades. Although more biased towards a single server, albeit with shared nothing architectures. The technology predates the more modern Apache-based systems, for lack of a better term, but it doesn't mean that they cannot scale across multiple processors. New databases such as Hive, Redshift, BigQuery, and PrestaDB provide as cloud-based interfaces in a more modern, horizontally scalable sense, at least for queries. A lot of work is going on in the Postgres role to support parallel processing there. An example of databases such as Greenplum, Netezza, Vertica, and so on Belly, the idea that relational databases do not scale across multiple independent processes. Very interesting. Cost of horizontal scalability is mostly a function of hardware provisioning and server hosting, and much removed from the software used for the database system. In my opinion, yes, NoSQL databases are meant to be able to horizontally scale more easily, but that doesn't necessarily mean more cheaply. In fact, I believe in a lot of cases there is an inverse relationship between cost and ease of implementation. For example, there's so many database systems in existence currently. I don't doubt for every easy to implement horizontally scaling modern NoSQL database system, there's a cheaper horizontally scaling relational database system. And the trade-off that is likely a harder to achieve goal in such system. Less well implemented dataset and less commonplace. Assume it is still cheaper to horizontally scale in relational DB than it is to scale it vertically. I believe this should generally be true either in the context of relational database. Horizontal scaling typically involves multiple servers, which means more hardware provisioning, disk memory, and CPU all at once than vertically scaling single server, since usually further provisioning is needed as a result of not all resources being exhausted at one time, rather a particular resource stopping out instead. There are some ratios that explain the vertical horizontal scaling costs for relation systems and NoSQL systems. Unfortunately, I don't think you'll be able to find an answer to that, being that's just too broad of a question with too many variables, such as the many choices of how to provision a server the OS use, if it is cloud, with the many options available, offsite or locally hosted and maintained. To come to a practical answer here, you'd have to analyze the cost efficiency versus ease of implementation. Yeah, I'm studying this stuff here. Let me see if I have the site. So there is this site here. I'm looking for a job, and this site, they connect people that are looking for jobs with people that are hiring, and they have these several tests here. And 3 months ago, I did a bunch of these tests, and I took a bunch of notes about what they're asking to study later. And now I'm studying this because a bunch of these tests I did it just to see what they were asking for, to know what's important. And now I'm studying this, and I'm also gonna do Kaggle competitions as well. So I'm dividing my time between solving the Kata's challenges and then studying this stuff. And I also have other projects on Web3 that I'm also doing. So usually I divide my time. I try to divide it by using the 80-20 rule, where 20% of my time I'm going to devote to the challenges and 80% to the projects. That way I achieve balance, and because the challenges are good for the more fundamental stuff on algorithms, and the projects are better for integration and design. And I want to improve on everything, obviously. Yeah, but the hard thing for me to balance is because I have too much stuff going on in my mind, so it's difficult to maintain focus. So yeah, but I will study I'm gonna watch this playlist here and the next few days, and then I'm gonna try once more to do the challenge, and if I can't do it, I'm just gonna look at the solution. But I've seen some solutions from other people on using how the algorithm works for the Gaussian elimination, but I still couldn't figure out how to implement it here. I didn't understand really well this B stuff, because this is supposed to be the elimination, and then you have the propagation, which after you eliminate to have the equation, then you need to figure out the values for x on that equation. And I couldn't figure out how to do it. But I think I will try another time. Yeah, so thanks for the wishes. Good luck wishes. The summations that explain the vertical, horizontal scaling costs for relation systems and NoSQL systems. Unfortunately, I don't think you'll be able to find an answer to that, being that's just too broad of a question with too many variables, such as the many choices of how to provision a server, the ones used, if it's cloud, the many options available offsite or locally hosted and maintained. See you, man. I'm not sure why I wrote this one though, but I'll search for it. And I think I'm gonna go to the next topics because I think I already understand this now, the differences. Might be a good idea to finish the other thing that I was doing as well, with integrating the Web3 stuff with SQL databases. And then I don't think I'm gonna display it on the browser with the animation, because I don't have time for that probably. But I think I could look it up how to connect the Flask with SQL. It's probably gonna be done through the SQL Alchemy stuff. But I still don't understand really well how the connection between the queries on SQL databases work with Python to do the calculations. So maybe that's something I should look into. And also when to connect different database types, like the other ones that I have here. These ones are probably more to more large storages, and SQL smaller storages. And there is this relationship between the size of the storage and how fast it is. So probably on big projects is a funnel, and I have to understand how the connection of the funnel works better in Python. Many people believe NoSQL should be ancient technology in the world of database. However, NoSQL is considered a baby, even though it's been around since the early 70s. How is that possible? Profit when both Google and Amazon. Blah, blah, blah. SQL databases have a predefined schema, while NoSQL databases are dynamic and perfect for unstructured data, though it's not mandatory. Today we'll have a look at one of the less complex NoSQL database management systems, wide column stores, also known as column families. This NoSQL model stores that in columns rather than rows. Thus, it's perfect for queries and less than optimal for large sets of data. Yeah, so NoSQL is better for faster, like Redis or MongoDB, I think. Then SQL is better for big data, probably. Then we'll go through the following explanations. Yeah, because SQL can create more connections between the data because it's stored on a table format. And NoSQL is faster because it's key value pairs, but then you lose the accuracy probably. Different NoSQL database management systems. First, let's take a look at the 4 main NoSQL database management systems. It will help us get a better idea of why column families are so popular. Key value stores. The simplest type are key value stores. Redis is one example. Every single item is given an attribute name, key, and value. Document databases. Document databases such as MongoDB associate key with a complex data schema known as a document. Nested documents and key array value pairs are containable inside each document. Graph databases and graphs. Wide column stores structure data around columns rather than rows. HBase and Apache Spark are 2 examples. Typically, column families are spotted, multiple columns used in unison in a similar way to relational database tables. Wide column stores use the typical tables, columns, and rows, but unlike relational databases, columnar formatting and names can vary from row to row inside the same table. And each column is stored separately on disk. Columnar databases store each column in a separate file. One file stores only the key column. The other only the first name, the other the zip, and so on. Each column in a row is governed by auto-indexing. Each functions always as an index, which means that a scanned queried column's offset corresponds to the other column no offsets in that row in their respective files. So I think it's very similar to the other one, but the only difference is that each row of each column works as its own index. And on the relational one, there's a primary key and different types of keys, depending on the table. Relational row-oriented storage gives you the best performance when querying multiple columns of a single row. Of course, relational databases are structured around columns that hold very specific information, upholding that specificity for each entry. For instance, let's take a customer table. Column values contain customer names, addresses, and contact info. Every customer has the same format. Columnar families are different. They give you automatic vertical partitioning. Storage is both column-based and organized by less restrictive attributes. RDB tables are also restricted to row-based storage and deal with tuple storage in rows, accounting for all attributes before moving forward. Columnar type storage can integrate columnar relational models, even though they also consider a part of NoSQL. Key value stores, columnar relational models, advantages and disadvantages. Allow for improved compression of attributes when stored in an attribute-wise manner. Each file is of the same data file. say you want to update a specific tuple for multiple attributes, or DB models can do this faster, and the fact that columnar families group attributes as opposed to takes more, blah, blah, blah. I think I'm gonna move on to the next topic. Kinda get at this, no? Once I'm done with these topics here, I'm probably gonna focus only on the projects because it's easier to learn, better to learn by doing the projects. Open source distributed event streaming platform used by thousands of companies for high performance data pipelines, streaming analytics, data integration, mission critical applications. Deliver messages at network limited throughput using a cluster of machines with latencies as low as 2 milliseconds. It's your production cluster. Availability. So it's a framework, probably. So maybe I'm gonna watch a video about this. The open source software platform developed by LinkedIn to handle real-time data is called Kafka. Oh, real-time data. Interesting. I think I was looking for that on the project that I was doing with the Web3 Ethereum information. It publishes and subscribes through a stream of records and also is used for fault-tolerant storage. The applications are designed to process the records of timing and usage. Log partitions of different servers are replicated in Kafka. It stores, reads, and analyzes the streaming data where developers and users contribute decoding updates. It is used for messaging, website activity tracking, log aggregation, and commit logs. It can be used as a database, but it does not possess a data model or indexes. So this brings me the question of how to integrate this with databases. I guess it's kind of like it's similar to the way that React is to JavaScript, where it's just a framework. Its growth is exploding exponentially. Let's see some facts and stats to underline our thoughts better. It enjoys a prime preference by more than 1/3 of the Fortune 500 across the globe. It is used for real-time data streams, collecting big data or doing real-time analysis or both. Oh, so that's exactly what I was searching for that time. It is used with in-memory microservices to provide durability, and it can be used to feed events to CEP, complex event streaming systems, and IoT style automation systems. How does Kafka work so easy? Driven by simplicity would be the right way to define the performance. It is easy to figure out how Kafka works with such easy from its setup and use. This increased performance in behavior is dedicated to its stability. It's provisioned to reliable durability with its flexible inbuilt capability to publish or subscribe or queue maintenance. This is crucial to have if you need to deal with n numbers of clients group. You have to show robust replication in the market to provide your customer with a consistent approach. Kafka's crucial behavior that set it apart from its competitors is its completely live systems with data streams. Its process enables the systems to be aggregate, transform, loaded or stores for convenience working. Successional for an additional. think one thing I could try to do is integrate that with the data I was receiving there from Web3. I think I'm gonna structure this depending on how long does it take to, because I've never done, the only Kaggle competition I've done was the easy one, the introductory one. So I'm not sure how long it's gonna take for me to finish a full competition, but I'm thinking about doing maybe 2 or 3 or something like that. And then maybe after I do these competitions, then I go back to this and try to integrate this database, this format, use Kafka with a database to display the information of Ethereum or the other protocols. It might be good as well to push that to GitHub and clone the repository on the virtual machine. That way I can separate the Web3 stuff on the virtual machine and the AI and data analysis stuff on the... But I think I'm gonna try to mix both, probably. It relies on OS kernels for moving the data more quickly and works on the principle of zero copy. It allows data records to batch into chunks, which can be synced from the file system to consumers. The facility to batch data gives an efficient data compression with I/O latency reduction. It has the ability to scale horizontally via sharding. This is also something I've seen on Ethereum when reading stuff about proof of stake. You can shard a title log into hundreds of partitions to thousands. This allows it to handle the massive workload easily. There are operations in which the CPU does not perform the task of copying data from one memory area to another, or in which unnecessary data copies are avoided. Saves CPU cycles and memory bandwidth many time-consuming tasks. Principles, blah blah blah. Okay. If your company plays with huge sets of data regularly, you need Kafka. There's a long list of companies using it. There's a long list of companies from Uber to Spotify and Goldman Sachs. Advantages given high throughputs, sorry. I don't know how to say this.
Throughput.
Okay. You can easily handle a large volume of data when generating at high velocity is an exceptional advantage in Kafka's favor. This application lacks huge hardware to support message throughput at a frequency of thousands of messages per second. Low latency handling this high volume message generation. Fault tolerance. This feature is handy as an inherent capability to be treated by a node built into a cluster. Durable. It is very durable in its operation and is so why many MNCs, I don't know what is this. Talking to durability requires skills. There's no special requirement for being a Kafka professional, but we have underlined some streams and professionals. Want to make a career in big data streaming and wants to accelerate their career. Testing professionals have a good scope in Kafka. It's blah blah blah. For the purpose of data tracking and manipulating them as per the business need, it is preferred worldwide. It gives the possibility to stream data in real time with real-time analytics. It is fast, scalable, and durable, and designed as fault tolerance. There are multiple use cases present over the web, where you can see why JMS, RabbitMQ, and AMQP are not even considered to work with, as the need is to operate huge volumes and responsiveness. Has high throughput, reliable setup with scope, blah blah blah. So now I think it's better to read about the integration. C, C++, Go, Java. Yeah, assume. Nice. Makes sense. Is server languages. Probably Rust works as well. Yeah, Rust. So any server language works. Yeah, I guess each language has its own library to handle the integration of the language with the framework for the database. Kafka is a database structure, from what I understand. I can also go on the website and click on get started or docs, API configuration, implementation. I wonder if you have to pay as well.
Hi, I'm Tim Berglund with Confluent. I'd like to tell you what Apache Kafka is, but first I want to start with some background. For a long time now, we have written programs that store information in databases. Now, what databases encourage us to do is to think of the world in terms of things. Things like, I don't know, users, and maybe a thermostat, that's a thermometer, but that's the idea, maybe a physical thing like a train. Let's see, here's a train. Things. There are things in the world. Database encourages us to think in those terms, and those things have some state. We take that state, we store it in the database. This has worked well for decades, but now some people are finding that it's better, rather than thinking of things first, to think of events first. Now, events have some state too, right? An event has a description of what happened with it, but the primary idea is that the event is an indication in time that the thing took place. Now, it's a little bit cumbersome to store events in databases. Instead, we use a structure called a log, and a log is just an ordered sequence of these events. An event happens, and we write it into a log, a little bit of state, a little bit of description of what happens, and that says, hey, that event happened at that time. As you can see, logs are really easy to think about. They're also easy to build at scale, which historically has not quite been true of databases, which have been a little cumbersome in one way or another to build at scale. Now, Apache Kafka is a system for managing these logs. Using a fairly standard historical term, it calls them topics. This is a topic. A topic is just an ordered collection of events that are stored in a durable way. Durable meaning that they're written to disk and they're replicated. They're stored on more than one disk, on more than one server, somewhere, wherever that infrastructure runs, so that there's no one hardware failure that can make that data go away. Topics can store data for a short period of time, like a few hours, or days, or years, or hundreds of years, or indefinitely. Topics can also be relatively small, or they can be enormous. There's nothing about the economics of Kafka that says that topics have to be large in order for it to make sense, and there's nothing about the architecture of Kafka that says that they have to stay small. So they can be small, they can be big, they can remember data forever, they can remember data just for a little while, but they're a persistent record of events. Each one of those events represents a thing happening in the business. Like remember our user, maybe a user updates her shipping address, or a train unloads cargo, or a thermostat reports that the temperature has gone from comfy to is it getting hot in here. Each one of those things can be an event stored in a topic, and Kafka encourages you to think of events first and things second. Now, back when databases ruled the world, it was kind of the trend to build one large program. We'll just build this gigantic program here that uses one big database all by itself. And it was customary for a number of reasons to do this, but these things grew to a point where they were difficult to change and also difficult to think about. They got too big for any one developer to fit that whole program in his or her head at the same time. And if you've lived like this, you know that that's true. Now the trend is to write lots and lots of small programs, each one of which is small enough to fit in your head and think about and version and change and evolve all on its own. And these things can talk to each other through Kafka topics. So each one of these services can consume a message from a Kafka topic, do whatever its computation is that goes on there, and then produce that message off to another Kafka topic that lives over here. So that output is now durably and maybe even permanently recorded for other services and other concerns in the system to process. So with all this data living in these persistent real-time streams, and I've drawn two of them now, but imagine there are dozens or hundreds more in a large system, now it's possible to build new services that perform real-time analysis of that data. So I can stand up some other service over here that does some kind of gauge, some sort of real-time analytics dashboard, and that is just consuming messages from this topic here. That's in contrast to the way it used to be, where you ran a batch process overnight. Now, it's possible that yesterday is a long time ago for some businesses now. You might want that insight to be instant or as close to instant as it could possibly be. And with data in these topics as events that get processed as soon as they happen, it's now fairly straightforward to build these services that can do that analysis in real time. So you've got events, you've got topics, you've got all these little services talking to each other through topics, you've got real-time analytics. I think if you have those four things in your head, you've got a decent idea of kind of the minimum viable understanding, not only of what Kafka is, which is this distributed log thing, but also of the kinds of software software architectures that Kafka tends to give rise to. When people start building systems on it, this is what happens. Once a company starts using Kafka, it tends to have this viral effect, right? We've got these persistent distributed logs that are records of the things that have happened. We've got things talking through them, but there are other systems. I mean, what's this? There's this database. There's probably going to be, another database out there that was built before Kafka came along, and you want to integrate these systems. There could be other systems entirely. Maybe there's a search cluster. Maybe you use some SaaS product to help your salespeople organize their efforts. There's all these systems in the business, and their data isn't in Kafka. Well, Kafka Connect is a tool that helps get that data in and back out. When there's all these other systems in the world, you want to collect data, so changes happen in a database, and you want to collect that data and get it written into a topic like that. And now I can stand up some new service that consumes that data and does whatever computation it needs on it. Now that it's in a Kafka topic, that's the whole point. Connect gets that data in. Then that service produces some result, which goes to a new topic over here, and Connect is the piece that moves it to whatever that external legacy system is here. So Kafka Connect is this process that does this inputting and this outputting, and it's also an ecosystem of connectors. There are dozens, even hundreds of connectors out there in the world. Some of them are open source, some of them are commercial, some of them are in between, but they're these little pluggable modules that you can deploy to get this integration done in a declarative way. You deploy them, you configure them, you don't write code to do this reading from the database, this writing to whatever that external system is. Those modules already exist, the code's already written, you just deploy them, and Connect does that integration to those external systems. And let's think about the work that these things do. These services, these boxes on drawing, they have some life of their own, they're programs, right? But they're going to process messages from topics, and they're going to have some computation that they want to do over those messages. And it's amazing, there's really just a few things that people end up doing. Like, say you have messages, these green messages, you want to group all those up and add some field, like come up with a total weight of all the train cars that passed a certain point or something, but only a certain kind of car, only the green kinds of cars. And you've got these other, say you've got these orange ones here. So right away we see that we're going to have to go through those messages, we're going to have to group by some key, and then we'll take the group and run some aggregation over it, or maybe count them, or something like that. Maybe you want to filter, maybe I've got this topic, and let's see, make some room for some other topic over here that's got some other kind of data, and I want to take all the messages here and somehow link them with messages in this topic, and enrich, when I see this message happen here, I want to go enrich it with the data that's in this other topic. These are common things. It's the first time you thought about it, that might seem unusual, but those things, grouping, aggregating, filtering, enrichment, enrichment, by the way, goes by another name in database land, that's a join, right? These are the things that these services are going to do. They're simple in principle to think about and to sketch, but to actually write the code to make all that happen takes some work, and that's not work you want to do. So Kafka, again, in the box, just like it has Connect for doing data integration, it has an API called Kafka Streams. That's a Java API that handles all of the framework and infrastructure and kind of undifferentiated stuff you have to build to get that work done. So you can use that as a Java API in your services and get all that done in a scalable and fault-tolerant way, just like we expect from modern applications to be able to do. And that's not framework code you have to write. You just get to use.
I think I sort of understand this when I watch this
Previous
video.
demo, you saw how we
I don't think I'm gonna spend a lot of time on this.
downloaded a
I'm gonna spend more time probably when I try to integrate this through the project that I'm doing, because I'm gonna learn a lot more by doing that. And then I'm gonna jump to this one, Spark. And then I'm gonna search this and choose the competition, and then I'm probably gonna do the rest. Watch these other videos on
bundle
stream.
of Kafka tools and scripts, and we used some of them to start a Kafka server. Then we used a few of the scripts inside to create a topic, read from a topic, and write from a topic. Now, it's great for demonstrations, but if we want to use this inside of Python, we would have to use some Python libraries in order to interact with Kafka. That way, our applications can interact with Kafka programmatically. Now, to start off, I still have the Kafka server running, and I still have the Zookeeper broker running. This means that Kafka is still running and available on my local machine. Now, to start off by using Python to act as a consumer or a producer, I have to install the package for using Kafka in Python. You'll see that I already have this installed, Kafka-Python, but if I were to install it from scratch on a new environment, I would type in pip install Kafka-Python, and this will install it. And again, this is already installed, so nothing happened on my computer. Now, I have two files prepared on this machine. The first one is called producer.py, and the second one is called consumer.py. As you can imagine, one is used for reading messages from Kafka topics, and the other one is used for writing messages to Kafka topics. So I'm going to be starting the first one, consumer.py. Let's take a look at what's inside of this file. This file is very simple. We take Kafka and we import the Kafka consumer. Then we have the topic name. Our topic name is named items. We have a consumer. The consumer is equal to Kafka consumer connecting to a topic. By default, it will connect to the correct port on localhost if nothing is specified. Now, this will start a loop and read the messages as they come in from the consumer. This will essentially be an infinite loop and will read messages as they come in. As the messages come in, we'll be printing them out to the console. So now that we've seen what's inside the file, let's run it. To run it, I go python consumer.py. This launches behavior very similar to the script that came in with the Kafka files that we downloaded. It will wait here for messages to come in and print as they arrive into the topic. I've opened up a new terminal. It's in the same directory, and we'll use this terminal to look at the producer. We've set up a topic name, and again, the topic name is items. The Kafka server, we've defined it. Following, we have the line producer.send with the topic name and a message. This line is telling us that for the topic name, items, lastly, we have in one request. Now that we've gone over what's inside this file, let's run it. Data structure, but we can see some more sophisticated designs where we have to optimize for certain use cases, such as some other
So it works pretty much like any API.
Hi, I'm Tim Berglund with
I think this is the last video that I'm gonna watch on this, and then I'm gonna go to the Spark stuff, do the rest.
I'd like to tell you what Apache Kafka is, but first I want to start with some background. For a long time now, we have written programs that store information in databases.
And I think this is the video that I just watched, but I want to watch again.
Now, what databases encourage us to do is to think of the world in terms of things. Things like, I don't know, users, and maybe a thermostat, that's a thermometer, but you get the idea. Maybe a physical thing, like a train. Let's see, here's a train. Things. There are things in the world. The database encourages us to think in those terms, and those things have some state. We take that state, we store it in the database. This has worked well for decades, but now some people are finding that it's better, rather than thinking of things first, to think of events first. Now, events have some state too, right? An event has a description of what happened with it, but the primary idea is that the event is an indication in time that the thing took place. Now, it's a little bit cumbersome to store events in databases. Instead, we use a structure called a log, and a log is just an ordered sequence of these events. An event happens, and we write it into a log, a little bit of state, a little bit of description of what happens, and that says, hey, that event happened at that time. As you can see, logs are really easy to think about. They're also easy to build at scale, which historically has not quite been true of databases, which have been a little cumbersome in one way or another to build at scale. Now, Apache Kafka is a system for managing these logs. Using a fairly standard historical term, it calls them topics. This is a topic. A topic is just an ordered collection of events that are stored in a durable way. Durable meaning that they're written to disk and they're replicated. They're stored on more than one disk, on more than one server, somewhere, wherever that infrastructure runs, so that there's no one hardware failure that can make that data go away. Topics can store data for a short period of time, like a few hours, or days, or years, or hundreds of years, or indefinitely. Topics can also be relatively small, or they can be enormous. There's nothing about the economics of Kafka that says that topics have to be large in order for it to make sense, and there's nothing about the architecture of Kafka that says that they have to stay small. So they can be small, they can be big, they can remember data forever, they can remember data just for a little while, but they're a persistent record of events. Each one of those events represents a thing happening in the business. Like remember our user, maybe a user updates her shipping address, or a train unloads cargo, or a thermostat reports that the temperature has gone from comfy to is it getting hot in here. Each one of those things can be an event stored in a topic, and Kafka encourages you to think of events first and things second. Now, back when databases ruled the world, it was kind of the trend to build one large program. We'll just build this gigantic program here that uses one big database all by itself. And it was customary for a number of reasons to do this, but these things grew to a point where they were difficult to change and also difficult to think about. They got too big for any one developer to fit that whole program in his or her head at the same time. And if you live like this, you know that that's true. Now the trend is to write lots and lots of small programs, each one of which is small enough to fit in your head and think about and version and change and evolve all on its own. And these things can talk to each other through Kafka topics. So each one of these services can consume a message from a Kafka topic, do whatever its computation is that goes on there, and then produce that message off to another Kafka topic that lives over here. So that output is now durably and maybe even permanently recorded for other services and other concerns in the system to process. So with all this data living in these persistent real-time streams, and I've run two of them now, but imagine there are dozens or hundreds more in a large system, now it's possible to build new services that perform real-time analysis of that data. So I can stand up some other service over here that does some kind of gauge, some sort of real-time analytics dashboard, and that is just consuming messages from this topic here. That's in contrast to the way it used to be, where you ran a batch process overnight. Now it's possible that yesterday is a long time ago for some businesses now. You might want that insight to be instant, or as close to instant as it could possibly be. And with data in these topics as events that get processed as soon as they happen, it's now fairly straightforward to build these services that can do that analysis in real time. So you've got events, you've got topics, you've got all these little services talking to each other through topics, you've got real-time analytics. I think if you have those four things in your head, you've got a decent idea of kind of the minimum viable understanding, not only of what Kafka is, which is this distributed log thing, but also of the kinds of software architectures that Kafka tends to give rise to. When people start building systems on it, this is what happens. Once a company starts using Kafka, it tends to have this viral effect, right? We've got these persistent distributed logs that are records of the things that have happened. We've got things talking through them, but there are other systems. I mean, what's this? There's this database. There's probably going to be, another database out there that was built before Kafka came along, and you want to integrate these systems. There could be other systems entirely. Maybe there's a search cluster. Maybe you use some SaaS product to help your salespeople organize their efforts. There's all these systems in the business, and their data isn't in Kafka. Well, Kafka Connect is a tool that helps get that data in and back out. When there's all these other systems in the world, you want to collect data, so changes happen in a database, and you want to collect that data and get it written into a topic like that. And now I can stand up some new service that consumes that data and does whatever computation needs on it. Now that it's in a Kafka topic, that's the whole point. Connect gets that data in. Then that service produces some result, which goes to a new topic over here, and Connect is the piece that moves it to whatever that external legacy system is here. So Kafka Connect is this process that does this inputting and this outputting, and it's also an ecosystem of connectors. There are dozens, even hundreds of connectors out there in the world. Some of them are open source, some of them are commercial, some of them are in between, but they're these little pluggable modules that you can deploy to get this integration done in a declarative way. You deploy them, you configure them, you don't write code to do this reading from the database, this writing to whatever that external system is. Those modules already exist, the code's already written, you just deploy them, and Connect does that integration to those external systems. And let's think about the work that these things do. These services, a box of some kind, they have some life of their own, they're programs, right? But they're going to process messages from topics, and they're going to have some computation that they want to do over those messages. And it's amazing, there's really just a few things that people end up doing. Like, say you have messages, these green messages, you want to group all those up and add some field, like come up with a total weight of all the train cars that passed a certain point or something, but only a certain kind of car, only the green kinds of cars. And then you've got these other, say you've got these orange ones here. So right away we see that we're going to have to go through those messages, we're going to have to group by some key, and then we'll take the group and run some aggregation over it, or maybe count them, or something like that. Maybe you want to filter, maybe I've got this topic, and let's see, make some room for some other topic over here that's got some other kind of
It's
data.
pretty much like the ocean of data that connects the rivers from these applications here.
And I want to take all the messages here and somehow link them with messages in this topic and enrich. When I see this message happen here, I want to go enrich it with the data that's in this other topic. These are common things. It's the first time you thought about it. That might seem unusual, but those things, grouping, aggregating, filtering, enrichment, enrichment, by the way, goes by another name in database land. That's a join, right? These are the things that these services are going to do. They're simple in principle to think about and to sketch, but to actually write the code to make all that happen takes some work, and that's not work you want to do. So Kafka, again, in the box, just like it has Connect for doing data integration, it has an API called Kafka Streams. That's a Java API that handles all of the framework and infrastructure and kind of undifferentiated stuff you have to build to get that work done. So you can use that as a Java API in your services and get all that done in a scalable and fault-tolerant way way, just like we expect from modern applications to be able to do. And that's not framework code you have to write. You just get to use it because you're using Kafka. Now, if you're a developer and you want to learn more, you know the thing to do is to start writing code. Check those things out. Let us know if you have any questions, and I hope we hear from you soon.
Okay, nice. So I think I'm gonna move on to once I start working on the project again, I'm gonna probably try to use Kafka and SQL, probably. To integrate the information that I was getting from the Web3, the Uniswap contracts. And I think I'm gonna have to refactor that code as well. I remember it was really slow and I didn't know exactly what was going on, so check out the Kafka package for Python. This should get you set up to string data from Kafka. So there's the documentation here. It doesn't look that... it doesn't seem that is that difficult. The most difficult part probably is connecting this with the other stuff that you have. That so far in the projects that I've done, that has been the most difficult part. And also figuring out the deployment and stuff like that. The integration is always the most difficult one. But each separate thing is relatively easy. So I think the consumer is the one that gets the data from Kafka, probably. The producer sends the data to Kafka. So I would be building the producer, probably. I would be building both, actually. The producer from the backend and then consumer from front end. Yeah, I'll look into this later. Apache Spark is a multi-language engine for executing data engineering, data science, and machine learning on single-node machines or clusters. Batch streaming data. Unify the processing of your data in batches and real-time streaming using your preferred language: Python, SQL, Scala, Java, or R. Execute fast, distributed NC SQL queries for dashboarding, and ad hoc reporting runs faster than most data warehouses. Data science at scale. So I think what I have to search is the difference between Spark and Kafka. So I'm probably gonna watch a video about this. First, the introduction to Spark, then comparing the both.
So Apache Spark is another kind of framework for doing big data processing distributed across clusters, like Mapreduce. The differences kind of come in how the computations are done. So, for example, with Spark, you've got a lot more flexibility in the computations. So with Mapreduce, you've got to do map and then reduce. Like, there's no way of getting around it. But in Spark, they provide like a load of different operations that you can do on the data, such as joins between different data structures.
Why would I use Spark?
Its purpose is to process large volumes of data, so it's maybe data that's not going to fit on a single node, but it's also computations over a large volume of data. You don't want to go through and sequentially do that. And if you've got parts of your computation that are independent of each other, and so you can do it on the data items individually, you can split that data across the cluster. and then do the computations on that single node, exactly like with Mapreduce. It's the data locality principle again. Do the computations on the node where the data is stored, and then you reduce those results down to what you want. The main programming structure that you're going to be dealing with is called a resilient distributed dataset, which is usually shortened to RDD, which is kind of a collection of objects that are spread across a cluster. But as a programmer, when you're dealing with that, you're kind of just interacting with it as if it's on a single node, so it's kind of hidden from you. This is distributed. In a Spark cluster, you'll have a driver node and then several worker nodes. And the driver node is running the main program that kind of has all of the transformations that you want to do to your data. And then these kind of get sent out to the worker nodes, who then operate that on the chunks of data that they have. In Spark, the transformations can be similar to Mapreduce, so it still provides the same map function and reduce functions. But then you have additional stuff on top of that, so they give you a filter operation directly. So you don't have to implement that. You can just call the filter function on RDD and say, I only want to return objects for which this is true. So here we've just got a very, very simple Spark example of just loading in a text file from a local file system, and we're just going to go through and count the number of occurrences of each word. This is exactly the same as the Mapreduce example we looked at last time, but we're doing this in Spark this time. Okay, so at the start, we set up a Spark config. So we just set the app name, which allows us to see which of our jobs is currently running within the web UI. We then set the Spark master, so because we're running this locally on a single computer, that's just local. We then set up a Spark context, which gives us access to the Spark functions for dealing with RDDs. We first of all need to load our data into an RDD, so we do this using the text file function, and that puts the contents of that text file into an RDD. The RDD you can kind of just view as like an array if you want to. It's kind of like an array distributed across the cluster. So here we've got our lines RDD. Each element in the RDD is a single line from the text file. We then go through and split each line using the flat map function. So that maps a single function over every single item in the data set. So every line, we go through, split it up into words, and then because we're using flat map, that then takes that from an RDD of arrays to an RDD of strings again. We then go through and exactly the same as in the Mapreduce example, we use the map function to map each word to a key value pair where the key is the word and then the value is the value 1. So in case we've got one instance of that word at that point. That then gives us a new RDD, and for that one, we go reduce by key. Instead of doing Mapreduce, that would just be reduce. But here in Spark, if we just did reduce, it would give us a single value for the entire RDD back at the driver. Reduce by key takes an RDD of key value pairs, and for each key, you give it a function to apply to those values for how you want it to be combined. So for us, we want to add up the number of those instances of that word that we have. So we use just a simple plus to aggregate those values. So that finally gives us our word count RDD, which contains key value pairs of words and a number of instances of those words. And so we then call the collect function, which will bring that back to the driver node, and then for each one of those lines, we print them out. So we print out the counts for all those words.
So this at the moment, that code is written for something that might be on your own computer. How would it differ if it was on a cluster, on a server farm, or on a data center or something like that? How would that vary?
So if you're running this on an actual cluster and not just on your local computer, then rather than setting master within your code and setting it to run locally, what you would do is you would have Spark running on the cluster, and you would use something called Spark submit to submit your Spark jobs to Spark to then be run. So it's just a different way of running them, basically, rather than hard coding it within your program. Even though you're then running it on the cluster, the rest of the code would be the same. So the work that I've done with Spark has been kind of using it to analyze large volumes of telematics data coming off of lorries as they're driving around, and using the data from that to identify locations where incidents are occurring, such as if they're cornering harshly or braking harshly.
Outside of research, what sorts of things is Spark being used?
Yeah, so Spark is used quite a lot in real world. Like you would find a lot of companies will be using it to kind of do large scale jobs on all the data that they have, and it can be used for like analysis or simply just processing that data and putting it into storage. The good thing about the distributed computing in clusters is that if you want to scale the program more, you just add more nodes to the cluster. So the point is, if you want to increase your processing power, you don't have to buy new hardware in terms of replacing your old hardware. You keep your old hardware, you buy new nodes and just stick them on the end, and you've instantly increased how much processing power you have. So if you suddenly say get a load more data that you need to process, and you think, oh, this current cluster size, that's not great, we can then expand that and then just add a few more nodes assisted in memory, which means
You're saying large amount of volumes of data.
I think I understand.
Spark as a data processing framework was developed at UC Berkeley's AMP Lab by Matej Saharia in 2009. In 2010, it became an open source project under a Berkeley software distribution license. In the year 2013, the project was donated to the Apache Software Foundation, and the license was changed to Apache 2.0. In February 2014, Spark became an Apache top-level project. By November 2014, Spark was used by the engineering team at Databricks, a company founded by the creators of Apache Spark, to set a world record in large-scale sorting. Now, Databricks provides commercial support and certification for taking the Spark programming test. At present, Spark exists as a next-generation real-time and batch processing framework. Let's try to understand what batch and real-time processing mean. We will use this information in the subsequent slides to compare Spark with Mapreduce, both of which are data processing framework in Hadoop. In case of batch processing, a large amount of data or transactions are processed in a single run over a time period. The associated jobs generally run entirely without any manual intervention. Additionally, the entire data is pre-selected and fed using command line parameters and scripts. In typical cases, batch processing is used to execute multiple operations, handle heavy data load, generate reports, and manage data workflow which is offline. An example is to create daily or hourly reports to aid decision-making. On the other hand, real-time processing occurs instantaneously on data entry or command receipt. It needs to execute within stringent response time constraints. An example is fraud detection. The need for Spark was created by the limitations of Mapreduce, which is another data processing framework in Hadoop. Let's see what these limitations are. Mapreduce is suitable for batch processing, where data is processed as a periodic job. Thus, it takes time to process data and provide results if the data is high. Depending on the amount of data and the number of nodes in the cluster to complete a job, it just takes minutes to process the data. However, it is not a good choice for real-time processing. Mapreduce is also not suitable for writing trivial operations, such as filter and join. To write such operations, you might need to rewrite the jobs using the Mapreduce framework, which becomes complex because of the key value pattern. This pattern is required to be followed in reducer and mapper codes. Mapreduce doesn't work so well with large data on the network. The reason is that it takes a lot of time to copy the data, which may cause network bandwidth issues. It works on the data locality principle, and hence works well on the node where the data resides. Mapreduce is also unsuitable for online transaction processing, or OLTP, which includes a large number of short transactions. Since it works on the batch-oriented framework, it lacks latency of seconds or subseconds. Additionally, Mapreduce is unfit for processing graphs. Graphs represent the structures to explore relationships between various points. For example, finding common friends in social media sites like Facebook. Hadoop has the Apache Giraffe library for such cases. It runs on top of Mapreduce and adds to the complexity. Another important limitation is its unsuitability for iterative program execution. Some use cases, like k-means, need such execution where data needs to be processed again and again to refine results. Mapreduce runs from the start every time as it is stateless executor. Spark is an open source cluster computing framework which addresses all of the limitations of Mapreduce. It is suitable for real-time processing, trivial operations, and processing larger data on a network. It is also suitable for OLTP, graphs, and iterative execution. As compared to the disk-based two-stage Mapreduce of Hadoop, Spark provides up to 100 times faster performance for a few applications with in-memory primitives. Fast performance makes it suitable for machine learning algorithms as it allows programs to load data into the memory of a cluster and query the data constantly. A Spark project comprises various components such as Spark Core and Resilient Distributed Datasets or RDDs, Spark SQL, Spark Streaming, Machine Learning Library or MLlib, and GraphX. Let's discuss the components of Spark. The first component, Spark Core and RDDs, are the foundation of the entire Spark project. They provide basic input-output functionalities, distributed task dispatching, and scheduling. Let's look at RDD closely. RDDs are the basic programming abstraction and is a collection of data that is partitioned across machines logically. RDDs can be created by applying coarse-grained transformations on the existing RDDs or by referencing external datasets. The examples of these transformations are reduce, join, filter, and map. The abstraction of RDDs is exposed similarly as in-process and local collections through a language-integrated application programming interface, or API, in Python, Java, and Scala. As a result of the RDD abstraction, the complexity of programming is simplified, as the manner in which applications change RDDs is similar to changing local data collections. The second component is Spark SQL, which resides on the top of Spark Core. It introduces Schema RDD, which is a new data abstraction and supports semi-structured and structured data. Schema RDD can be manipulated in any of the provided domain-specific languages, such as Java, Scala, and Python, by the Spark SQL. Spark SQL also supports SQL with Open Database Connectivity, or Java Database Connectivity, commonly known as ODBC or JDBC, server and command line interfaces. The third component is Spark Streaming. Spark Streaming leverages the fast scheduling capability of Spark Core for streaming analytics, ingesting data in small batches, and performing RDD transformations on them. With this design, the same application code set written for batch analytics can be used on a single engine for streaming analytics. The fourth component of Spark is Machine Learning Library, also known as MLlib. It lies on top of Spark and is a distributed machine learning framework. MLlib applies various common statistical and machine learning algorithms. With its memory-based architecture, it is 9 times faster than the Apache Mahoots Hadoop disk-based version. In addition, the library performs even better than VowPow Wabbit or VW. The VW project is a fast out-of-core learning system sponsored by Microsoft.
And so far, from what I understand, they are very similar. They both are handling data, big data.
The last component, GraphX, also lies on the top of Spark and is a distributed graph processing framework. For the computation of graphs, it provides an API and an optimized runtime for the Pregal abstraction. Pregal is a system for large
But Spark seems to be better for machine learning stuff.
scale graph processing. In-memory processing, implemented to decrease the in-memory size. Even beyond theoretical terms, distinct data source will likely support distributed in nature. Can be implemented using related system is more note that Spark does not need Hadoop. It just supports the storage systems that implement the. Another important advantage is that it integrates tightly, allowing you.
In this video, I'm going to show you why companies love to build their data science platforms on top of Apache Kafka and Apache Spark, because this is the reason you should get into Spark and Kafka. If you're new here, my name is Andreas. I'm a data engineer and data science platform architect. My passion is to bring you the best tips and tools for building your career and your reputation by becoming an awesome data engineer. On this channel, I do a lot of strategy videos and Q&A sessions, as well as tutorials, just like this one. So if you're new here, subscribe to the channel. You will not miss any updates. So in this video, I'm going to show you why companies love Kafka and Spark and why most data science platforms are using it. And one of the reasons is parallel processing and distributed processing. So that you don't have any bottlenecks in your system and you can very efficiently process data if it's stream processing or batch processing. If you look at data science platforms, one thing that most of them have, or all of them have in common is it starts with some kind of ingest. Ingest, where your data comes from the internet, let's say from an API. And then after that, it goes into some kind of a processing where Kafka and Spark are living. Kafka, a message queue, and Spark for the actual processing of the data. Then after the processing, it goes somewhere in a storage. This is mostly in data science platform, some kind of a distributed storage. If you're on a Hadoop platform, it goes, for instance, into HDFS, or it can go into a NoSQL database, like, for instance, HBase. HBase is, if you're already on a Hadoop platform, it's more or less built in, so it's very easy to use. And then from this on, it's going to be going in the direction of visualization. And for visualization, you can have a user interface, a web interface, or, for instance, what many people are also using are BI tools, like Tableau or like Power BI. Okay. The main thing here is to have this whole process as efficient as possible, so you don't have any bottlenecks and everything works in parallel. And how do you do that? What companies are doing is they use a platform with distributed processing. Let's say you have an API at the ingest phase. You have an API. This API, let's say REST API. This REST API runs on top of a server. And what you can have if you have in front of those servers a load balancer, you can have multiple servers here, and you can then distribute the load from the load balancer onto those servers. So this is the first stage, distributed. Next stage is going to be into some kind of a message queue, so you don't get into the situation where you're getting back pressure. That means you are you're getting a lot of data from the API and it cannot get processed as fast as needed. So with Kafka in the processing, so this is the ingest. With Kafka in the processing, in the previous tutorial, I've talked about topics and so on. With Kafka is also a distributed system, so you have a topic has multiple partitions, and the partitions are then distributed on top of the servers or on multiple servers. So you have multiple servers at Kafka, and it's also distributed. So if you post from an API into Kafka, this all goes parallel here. So then the next stage is the actual processing of the data. The actual processing, you do this, for instance, with Spark. And Spark, also Spark in-memory processing system for batch and for stream processing. So if you're doing stream processing, in this example, Spark is a distributed system. You have multiple servers running on Spark. And if you're getting data from Kafka, this means you're starting a direct stream from Kafka, and then this is also parallel. So this goes here. Each server from Kafka is posting.
So I think I understand now. That's the biggest question I had when I was doing the project there. And that's why I wasn't sure if I should do it with CSVs or SQL. But it looks like the best way is probably to get the data stream from the contracts, from the smart contracts, and then send them to Kafka. And from Kafka, send them to Spark, run machine data analysis on Spark, and then from Spark send to the other ones to visualize.
In parallel into Spark workers. So then you're in parallel. You don't have any bottlenecks here. The next phase would be store the data. Store the data. You do, let's say, HDFS. Store data from Spark into HDFS. HDFS is Hadoop distributed file system. This means you have multiple servers again, and you're running the storage on top of the servers. I think you can see a pattern emerging here. So this also goes from Spark in parallel to HDFS. What you also do in Hadoop environments is you're running the Spark workers on top of the data nodes from HDFS. So it's even faster because you don't have that much of a travel, or you don't need to send as much data to HDFS or to Spark. And then the data is stored, the data can be processed. If you then go and say, okay, I'm going to do a batch processing, then what happens is then those two are also going to matter. And Spark is going to load the data in parallel from HDFS, which is stored in parallel, and you have the full potential of the whole platform. And so, yeah, this is how it works. And then let's say you have on top of HDFS, you can, for instance, then have here a Hive server or a let's keep it simple with Hive, and then you have a visualization with a SQL interface with Tableau. Either with Tableau, or you could access it from a UI, or you could write this out from Spark into HBase and then have it accessed from a UI. Okay, but yeah. So this is the idea that the processing is completely in parallel. Everything is in parallel, and it's very efficient. It's very fast. And this is why people are going to use Kafka and Spark a lot, because it's super scalable. It's super efficient. It's very practical. Also, if you're doing streaming, it's not that the only way here is to go from Kafka into Spark and then further into a storage solution. What you can also do is you can go out from Spark and you can again put it into a Kafka topic. So you can chain all those things together and have a super large pipeline. You can do this multiple times and refine your data even more. Yeah. So this is the reason a lot of people are using Kafka and Spark. It's very, very versatile and very, very performance oriented for distributed systems. Okay, so that's it for the reasons you have to learn Kafka and Spark. Tomorrow is going to be part 2 of the tutorial. It's how you install a dev environment for Spark. This is going to be a lot different than many other tutorials you're seeing. We're not going to use the Spark console. We're not going to go into coding with dev environments, with IDEs. We're going to do this with Apache Spark. Something very different and something very cool, because I use this to learn Spark myself, and I'm giving a lot of people the advice to do this as well, and it's working. If you want to learn more about the...
So this answers a lot of the questions that I had. I think I'm gonna watch this one. Probably read this through and then watch that one, and then choose which competition I'm gonna do on Kaggle. I'll probably try to do the projects first and then watch these videos if I'm having too much trouble doing the project. But now I think it's a lot more clear in my mind what I should do. I should figure out how to connect the data from the contract, from the DAXs to Kafka, and then use the data from Kafka to Apache, then run whatever computation I want to run on Spark, and from Spark send to SQL, and from SQL, or either SQL or Redis, or some type of storage, and then from that display on the browser. Kafka versus Spark is the comparison of two popular technologies that are related to big data processing, are known for fast and real-time, or streaming data processing capabilities. Kafka is an open source tool that generally works with the publish-subscribe model and is used as intermediate for the streaming data pipeline. Spark is a known framework in the big data domain that is well known for high volume and fast unstructured data analysis. The basic storage components in Kafka is known as the topic for producer and consumer events, whereas Spark used resilient distributed dataset structure and data frames for processing the datasets. Kafka is an open source stream processing platform developed by the Apache. It is a mediator between source and destination for a real-time streaming process where we can persist the data for a specific time period. Kafka is a distributed messaging system where we can use that persisted data for the real-time process. It runs as a service on one or more servers. Kafka stores string of records in categories called topics. Each string record consists of key value and timestamp. So it's NoSQL format. To start Kafka server starts. Following are the main components of Kafka. Source, this will trigger when a new CDC, change data capture, or new insert occurs at the source. For that, we have to define a key column to identify that change. Broker, which is responsible for holding data. Each broker holds no number of partition. Topic, it categorizes the data. Topics in Kafka are always subscribed by multiple consumers that subscribe to the data written to it. To create a topic, create it like this. And to see the topic list. Partition topics are further split into partitions for parallel processing. Producer is responsible for publishing the data. It will push the data to the topics of their choice. The producer will choose which record to assign to each partition within the topic. Kafka has commanded to produce a message to a topic. That's what consumers will consume data from topics. A consumer will be a label with their consumer group. If the same topic has multiple consumers from different consumer group, then each copy has been sent to each group of consumers. You can sync with multiple sources to persist the data. Kafka has commanded to consume messages to a topic. You can use Flume Kafka sync, in which as soon as any CDC or new insert Flume will trigger the records and push the data to the Kafka topic. For that, we have to set the channel, same as Flume Kafka. Apache Spark is an open source cluster computing framework, originally developed at the University of California, Berkeley. The Spark code base was later donated to the Apache Software Foundation. Spark provides an interface for programming entire clusters with implicit data parallelism and fault tolerance. When Hadoop was introduced, Mapreduce was the base execution engine for any job task. In the Mapreduce execution, read-write process happened on an actual hard drive. This is the reason for the more time and space consumption at the time of execution. Apache Spark is an open source platform, improves execution quality than the Mapreduce process. It's an open platform where you can use several programming languages like Java, Python, Scala, R. Spark provides in-memory execution that is 100x faster than Mapreduce. This uses the RDD definition. RDD is a robust distributed data set that allows you to store data on memory in a transparent manner and to retain it on disk only as required. This is where the time to access data from memory instead of the disk is true. Spark is the platform where we can hold the data in the data frame and process it. Application developer, data science, data analyst can use the Spark to process the huge amount of data within a minimum period of time. We can use a feature like interactive, iterative analysis of data in Spark. Spark streaming is one more feature where you can process data in real time. The banking domain needs to track the real-time transaction to offer the best deal to the customer. Tracking suspicious transactions. Spark streaming is most popular in younger Hadoop generation. Spark is a lightweight API, easy to develop, which will help a developer to rapidly work on streaming projects. Spark streaming will easily recover lost data and will be able to deliver exactly once the architecture is in place, and without any extra coding efforts. We can work on real-time Spark streaming and historical batch data at the same time. In Spark streaming, you can use multiple tools like Flume, Kafka, RDBMs as source sync, or can directly stream from RDBMs to Spark. Can run Spark. So everybody, blah blah blah. Using Spark SQL is basic SQL queries to process the data. This Spark provides better features like MIB, MLib, machine learning library for data science predictions. So this is the comparison, I think. Apache Spark, 100 times faster than Hadoop, decent speed. You're trying batch processing, real-time window processing only. Difficulty, easy to learn because of high level, easy to configure. Recovery allows recovery of partitions using cache and RDD. Fault-tolerant replication. As interactive modes, no interactive mode consumes data. Key difference between Kafka and Spark. Let us discuss some of the major differences between Kafka and Spark. Kafka is a message broker. Spark is the open source platform. Kafka has producer-consumer topic to work with data, where Spark provides platform pull the data. Hold it, process, and push from source to target. Kafka provides real-time streaming window process, where Spark allows for both real-time streaming and batch process. In Kafka, we cannot perform a transformation, where in Spark we perform ETL. Kafka does not support any programming language to transform the data, where Spark supports multiple programming languages and libraries. So Kafka is used for real-time streaming as channel or mediator between source and target, where Spark uses for real-time string, batch processes, and ETL also. Features of Kafka versus Spark. Some key features are listed below. Data flow. Kafka versus Spark provides real-time data streaming from source to target. Kafka just flow the data to the topic. Spark is procedural data flow. Data processing. We cannot perform any transformation on data, where in Spark we can transform the data. Kafka persists data to some time as defined in the configuration. We have to use a data frame or dataset object to persist the data. ETL transformation. Using Spark, we can perform ETL where Kafka does not provide ETL. Memory management. Spark uses RDD to store data in distributed manner, i.e. cache local space, where Kafka store data in topic in a buffer memory. Conclusion, we can use Kafka as a message broker. It can persist the data for a particular period of time. Using Kafka, we can perform real-time window operations, but we can't perform ETL transformation in Kafka. Using Spark, we can persist the data in the data object and perform end-to-end ETL transformations. That's the best solution if you use Kafka as a real-time streaming platform for Spark. This has been a guide. Okay. So pretty much the same as the other one, as the video was saying. I don't think I need to read this one. It's gonna be redundant. I'm definitely gonna read a lot more about whenever I'm doing the projects. So now let me search for this last topic here. So these are different data formats. So I need to search for encoder for serialization. The issue with this, the way that I wrote this, I don't remember what was the question about, or is a little bit vague here. And of course I wrote it like this because I had no idea what this stuff was back then. But I guess I need to understand how to encode from this to the other types. RDDs, resilient data, something that I just wrote, just read about. Spark platform provides versus data frame versus data set API loads. That's RDD. That's for. Resilient distributed data set. Resilient distributed data sets. Maybe I should watch a video about this. Spark does not support performing actions and transformations on copies of RDDs that are created via deserialization. RDDs are serializable so that certain methods on them can be invoked in executors, but end users shouldn't try to manually perform RDD serialization. When an RDD is serialized, it loses its reference to the Spark context that created it, preventing jobs from being launched with it. In earlier versions of Spark, your code would result in a null pointer exception when Spark tried to access the private. The error message was worded this way because users were frequently running into confusing new pointer exceptions when trying to do things like this, which caused actions to be invoked on deserialized RDDs on executor machines. If anyone would try to manually deserialize their RDDs on the driver. So I can see how this error message could be slightly misleading. Interesting. So I'll watch this video.
Hello friends, welcome back. Spark streaming and Kafka streams. Before comparing both of these streaming frameworks, let's talk about why you need to do stream processing. The demand for stream processing is increasing every day. The reason is increasing of volume of data. Big volume of data. Just processing big volumes of data is not enough. The data needs to be processed quickly so that organizations can react to changing business conditions in real time. Stream processing is the real-time processing of data continuously and concurrently. Stream processing is the ideal platform to process data streams or event data, whereas complex event processing utilizes event-by-event processing and aggregation. For example, on potentially high ratio of event throughput versus number of queries, there might be out of order of events from a variety of sources, often with large about its takeoff time, the height, or further. So which will be used to petabytes of data processing. So if you want to process the data which is received from another Kafka topic and you process the data on your first used to build a machine learning model after receiving, and it can compute as per the machine learning model libraries in framework of Apache Spark like Mapreduce join. So using these functions, you can easily long range to the particular window. Go with PIs and some other databases. Simple and easy to integrate with other systems. Because if you want
I think I'm gonna watch these 2 videos here and then I'm gonna choose the competition. And then I'm done for today. I'll be right back.
Welcome to Bite-Sized Data Science. We left off our Spark discussion talking about RDDs, data frames, datasets, driver programs, and why you may want to use Spark. In this video, we'll go a bit deeper to get an understanding of how Spark works by looking at resilient distributed datasets. Don't worry, you don't need to be a hardcore software engineer to understand this. We said that a Spark client is a driver program that talks to a Spark server. That's not really different from you using your browser to view YouTube videos like this one or to access email. By the way, I've heard many times people say that Spark is easy. Keep in mind that it is still programming. You have to learn the classes and methods and know how to use them. As we saw earlier, an RDD is an abstraction of your distributed data. It has a few interesting features. First, it is immutable, which means that once created, it cannot be modified. This is convenient when it comes to resilience. When you execute operations that change an RDD, Spark creates a new one and keeps track of where it came from. For example, if you have your initial data in an RDD called RDD1, and you convert some fields from character strings to numbers, the new RDD, RDD2, will contain these modifications, but also remember the operation and that they operated on RDD1. So, if the creation of an RDD fails for any reason, it only needs to go back to the previous RDD and start from there instead of having to go all the way back to reading the data from disk. You may say that all these copies will eat up your memory quickly. That's possible, but Spark will manage memory and remove what is not needed. For example, if you are now at RDD3, do you really need to keep RDD1 since you have RDD2? Once RDD3 is created, do you really need to keep RDD2 around? Of course, it is a bit more complex since you could create RDD4 based on RDD1, for example. We can see that we can have quite a chain of RDDs, and with many branches, it starts looking like a tree. Let's say RDD1 is used to create RDD2 that converts a character date field into a datetime type, and then you use RDD2 and convert the salary character field into a floating number to end up with RDD3. Isn't that a waste of resources to read all the records twice? Yes, it is. There is space for optimization, and Spark does it. The operations on an RDD can be transformations or actions. The creation of RDD2 and RDD3 involves transformations. Since you're not doing anything with your data, Spark knows what you want to do, but does nothing. This is called lazy evaluation. Once you decide to really do something like return the average salary of all employees by department, then Spark starts doing all the transformations that are required for the action, the averages. This way, it can look at all the transformations and decide the most efficient way to get there. Why do you need to know this? That's because many people run into problems and don't realize that it is not the last action you took that is the problem, but many transformations before it. You may think, that's simple, I get it. Still, I guarantee that many of you will run into problems because of the lazy evaluation. After you spend many hours trying to figure out why your average fails and see the error in the previous transformation, you'll get it and be fine from that point on. The concept of lazy evaluation, transformation, and action also applies to data frames and data sets, so always keep that in mind. Here are examples of transformations. For example, you could decide to extract the distinct records from a file. This is noted, and the evaluation will happen later. If you are planning to send results back to the driver program, then it is an action and the execution must happen. When writing their code, people often add actions to their processing just to make sure the transformations are working. These extra actions can be removed once you're confident of your transformations. So, remember, Spark uses lazy evaluation, so errors can be anywhere since the last action. In the next video, we'll talk about data frames and Spark.
RDD versus data frame versus data set. When talking about the difference between RDD, data frame, and data set, almost all three of them provide most of the features. For example, RDD, data frame, and data set supports processing structured and unstructured data. All three support file formats like text file, CSV file, GSON, and Parquet file formats. All the three abstractions support accessing data from data sources. Again, all the three are immutable collections. Finally, the operations are lazily evaluated in all the three collections. Then what really is the difference between the three Spark abstractions? In this video, I'm going to tell you 7 concrete differences between these three abstractions. Let's start with the first one. 1. The RDD in data frame is a distributed collection of elements. However, in data frame, the data is organized into named columns. It is conceptually equivalent to a table in RDBMS. Dataset is an extension of data frame. 2. The RDD is a low-level abstraction that was introduced in Apache Spark 1.0 release itself, whereas the data frame was introduced in 1.3 release, and dataset abstraction was released in the 1.6 release. 3. Data frame doesn't provide compile time type safety. For example, if you try to access a column from data frame, which is not available, that doesn't throw error during compile time. It throws the error only when you try to execute the code. However, this is not the case with the dataset. Dataset throws the error as you type the wrong column name. This saves developer time and cost. Number 4. APIs like AG, select, sum, average are introduced in data frame and datasets. These operations make the code much more readable than the algebraic type operations in RDD. For example, look at the below word count program. Let's say RDD is a RDD that contains text for word count. DF is the data frame that contains the text for word count. All it does is calculate the number of times each word occurs. We can see that the operations on data frame are much more readable than the RDD counterpart operations. The goal here is not to show how to write word count program, but to show how readable the operations are when working in data frames compared to RDDs. 5. Data frames and datasets API are built on top of Spark SQL engine, and we can write SQL queries to access the elements, whereas Spark SQL cannot be used on RDDs. 6. Catalyst Optimizer is introduced in data frames, which optimizes the performance by regenerating most optimized physical and logical query execution plan. This results in more efficiency and speed. Datasets also leverages this functionality. However, RDDs doesn't have the benefit of Catalyst Optimizer. 7. RDDs doesn't use tungsten component, whereas dataset and data frames uses tungsten component, part of Spark SQL engine, that enables storing the data in off-heap memory in binary format. This provides 3 main advantages. A. Avoids garbage collection by storing the data in off-heap memory. B. Occupies less memory space. And C. Avoids expensive Java serialization by storing the data in binary format. 8. Dataset provides advanced encoders, which can provide on-demand access to individual attributes. Data frame doesn't have this feature. In the next video, let's look at how to join 2 datasets.
Okay, let's choose the Kaggle competition now. Don't remember what this is. I think I'm gonna close it. I think what I'm gonna do is watch this playlist and watch this playlist off stream and try to solve this off stream as well. And depending on, because I have a lot of other stuff to do, so depending on how much time I devote to this, if I can't do it, then next time I'm gonna try to do it on stream again, one more time. And then if I can't do it on stream, I'm probably gonna move on to the next challenge. And the remaining time, I'm gonna start whatever competition I choose here. So I think I'm gonna see if there are competitions for blockchain besides forecasting, because I don't think that works. Yeah, so it doesn't look like. It doesn't look there is any competition. Ideally, I would be able to find one so that everything is aligned. And the thing is that I don't know if this competition is how it works exactly. But because they have these price tags, I imagine that it's gonna be extremely hard. So I might have to put a filter there to find the ones that are for beginners. Yeah, crypto forecasting. Maybe I should try to do this, because why not? But it does. This kind of competition don't make any sense to me, because If you could do this, why would you do it for this price and not set up your own thing? Doesn't make sense. And I'm also not sure if I can participate on this. It looks like the data is here. Maybe I should try this one just because even if I like just not with the intention of winning but of learning, because I'm gonna be manipulating crypto data, which goes alongside the other goals that I have. So it's probably better than doing something that I'm not really interested on. I think I'm gonna end up choosing that one. I think I'm gonna go into the 9 page here, but I'm probably gonna choose this one. Hash code archive action. Yeah, the only issue if I choose that one is that I'm not sure how long it's gonna take until I finish. So I might have to do the 2 projects simultaneously. The competition and the other one that I was doing to learn the Kafka and Spark stuff on how to integrate the Kafka and Spark. And I think while I do this competition, I'm gonna research the methods that I have on the file here with the topics for our data analysis, and then I'm gonna perform these methods, all these methods here, along the competition, even if it doesn't make sense, just to practice this stuff here, finding the correlation, building different models. I think I'm gonna probably try to build a bunch of different models using the sklearn library. I mean, some of these challenges are ridiculous. Like 20,000, figure out how to make it, and I think it doesn't make any sense to me. Yeah, this one makes more sense. $1 million. And I wonder how it works, the prizes as well for this. How do they decide who wins, how it works? Okay, so this is the 9th. Maybe one more and then I'll look deeper into this one. Yeah, so let me look at this. Over 40 billion worth of cryptocurrencies are traded every day. They are among the most popular assets for speculation and investment, yet have proven wildly volatile. Fast fluctuating prices have made millionaires of a lucky few and delivered crushing losses to others. Those price movements have been predicted in advance. In this competition, you use your machine learning expertise to forecast short-term returns in 14 popular cryptocurrencies. We have amassed a dataset of millions of rows of high-frequency market data dating back to 2018, which you can use to build your model. Once submission deadline has passed, your final score will be calculated over the following 3 months using live crypto data as it is collected. The simultaneous activity of thousands of traders ensures that most signals will be transitory. Persistent alpha will be exceptionally difficult to find, and the danger of overfitting will be considerable. In addition, since 2018, interest in the crypto market has exploded, so the volatility and correlation structure in our data are likely to be highly non-stationary. The successful contestant will pay careful attention to these considerations and in the process gain valuable insight into the art and science of financial forecasting. G Research is Europe's leading quantitative finance research firm. We have long explored the extent of market prediction possibilities, making use of machine learning, big data, and some of the most advanced technology available, specializing in data science and AI indication for workforces. She researched for this competition. So the issue with this type of stuff is that I don't believe that the future is computationally reducible, so you can't predict the future or the price movements using computation. But maybe you can find patterns on human behavior, which is the interesting part to me. So I think this is, and also it has to do with crypto, so there's potential to mix this with the other project and do both at the same time. That's why I think this is the best one, probably, for me. Because eventually I also want to learn how to build stuff on Web 3.0. I think there's a lot of opportunity to find jobs there as well. So it just integrates everything that I'm trying to do.
Are you ready?
So it looks like it's finished already, but I'm not sure if I can participate or... Submissions are evaluated on the weighted version of the Pearson correlation coefficient. You can find additional details in the prediction details in the evaluation section of this tutorial notebook. You must submit to this competition using the provided Python time series API, which ensures that models do not peak forward in time. To use the API, follow this template in Kaggle Notebook. More detailed introduction to the API is available here. This is a forecasting competition with an active training phase and a second period where models will be run against real market data. Training timeline. So it started on last year, 2021, entry deadline. Set the competition rules before this date in order to compete. And so it looks like it's finished already. Yeah, it's already done. But maybe it's interesting anyway to do it. Nah, I can't do it. I think I'll do this off stream, obviously, because I don't wanna risk anything. Leaking anything.
Are Are you ready to test your skills against the best? Are you part of the 1%?
Yeah, that's the thing.
Able to see through the noise? G Research is laying down the challenge. Forecast future returns of 14 crypto assets in the first ever Kaggle competition of its kind.
That's why this stuff is so stupid. It doesn't make sense at all. Why would anyone do this for this price? But I guess for practicing purposes, it's probably good. Yeah, so I'm gonna choose this one probably, and I might change my mind later, but for now, this one is gonna be the one. And I'm probably not gonna stream for the next few days, so I'm probably gonna stream either Sunday or next week. And then I'm gonna do, if I haven't done this off stream, I'm gonna try this one. If I was able to finish, then I'm gonna do another challenge, and then with the remaining time, I'm gonna do this competition here and probably work on the other projects on Web3 8.0 so I can work on everything at the same time. So yeah, see you then.